Okay, so it's about to start. A very good morning, a very good afternoon to all. Today we have Dr. Mohammed Asim with us, who is going to share his expertise on modeling and design of photovoltaic cell through a webinar. And I hope you will like this session. And there are few rules of this webinar. All the participants will mute their mic. And after the session, if you have any question, just raise the hand, right? Just raise the hand and I'll ask you to put forward your questions. Okay, am I clear? So, welcome, sir. And let's start. And before starting, let me tell you that Dr. Mohammed Asim is a well-known author and he has numerous work on modeling and designing of photovoltaic cell. He has 2 patents also, which is registered in his name on the same topic. So it would be great to listen to him. Welcome, sir.
Is my PPT available to everyone?
Yes, sir, it is visible.
Good afternoon, everyone. Hope you all and your family members must be doing fine and must be safe in this tough situation. First of all, before starting the seminar, I would like to thank Dr. Vanya Arun ma'am, Head EC ILM Greater Noida, and Mr. Piyush Agarwal, coordinator of this event, Assistant Professor ILM Greater Noida, for conducting this webinar. As the topic of this webinar is modeling and design of photovoltaic cell. Am I audible to everyone?
Yes, sir. Very much.
The topic of this webinar is modeling and design of photovoltaic cell. Before going to the design and modeling of the photovoltaic cell, I would like to briefly discuss the history of it, then the introduction part in which we are discussing about the energy scenario and the challenges, then the modeling part, and finally we will be concluding. So world energy consumption scenario, if we see, it is much more dependent on fossil fuels, and we can see in the graph how the consumption of the fossil fuels have increased from the 1820s till now, and the major part is consumption is of oil and coal. Major part you can see in the graph, the green part is showing the oil consumption, and this red part is showing the coal one, and the rest, nuclear and hydro and other. This was the dependence on the fossil fuels. And this consumption of the fossil fuel had adverse effect on the environment and on us and on us also. So basically what we do, what are the effects you can see here in the graph, in the figure, that in this figure you can see that when oil was transported with the help of the large ships, and sometimes this oil used to spill on the water in the sea, and it used to disrupt the marine life there, to the fish and the other aquatic life there also get disturbed. Similarly, you can see the pollution, the smoke coming out of the chimneys of so many industries, and where coal and the rest of the fossil fuels are burning, and it harms it affects our pollution level. Similarly, you can see the ice also get melted, and in areas where ice is there, the ice keeps on melting, and it increases the water level in many areas, and in different parts of the world, lands are getting submerged due to this. And you can see the top right figure, in which you can see the ozone layer is getting depleted. There's 2 graphs are shown of the Earth. One is in 1982 and 2011, and you can see how much the ozone layer has depleted over there. And all this contamination, either it be air pollution or water pollution or the soil pollution, this ultimately is affecting our body. And this figure shows it. How the air pollution affects us, how the soil pollution affects us, how the water pollution affects us. In this figure, we can see the effect of all the pollutions. Ultimately, it is on our body, and this is due to the burning of the fossil fuels. So, and there have been other issues also in the history, for which we are not, our focus is shifting from these fossil fuels. you might have heard of the first oil crisis and the second oil crisis. This first oil crisis of 1973, it was in October 1973, and what happened in this organization of the Arab petroleum exporting countries, the countries which used to have more petroleum sources, proclaimed an oil embargo. Embargo is what an official ban or trade on the commercial activities. They proclaimed an oil embargo, which led to the increase in oil price to about 400% times. It increased about 400 times the oil price. So it is in the history. It is also known as oil crisis or oil shock. It was a shock to the world, and it is also known as first oil shock. Similarly, second oil crisis took place in 1979. During this time, they started the they stopped the development of they stopped increasing the fuel consumption, and during that time also the price also increased during the second oil crisis. So we are having pollution problem. The cost of the petrol is increasing, and there was some accident in the history. One in various accident happened in the history, which like nuclear disaster of Chernobyl accident, which happened in 26 April 1986. It was a nuclear disaster. Chernobyl is in you can say Ukraine. The country is known as Ukraine, SSR, and it is the world's worst nuclear disaster in the history. This 26 April 1986, and affected many lives. And after so many years, it kept on affecting the life of the people there. Similarly, the Fukushima nuclear disaster, it is in Japan. There also, when a tsunami and the earthquake hit that place, it also resulted in large disruption in the nuclear power plant, and many lives of people were affected. So all these things means the pollution problem, the oil crisis, the nuclear disasters, and the other disasters in the generation made the people of the world to think for another alternate source. So where to go? And then came the renewable energy sources. So people moved to renewable energy sources. There are various renewable energy sources available: wind, solar, tidal, ocean thermal, OTEC. There are many. Here we are concentrating on solar energy. These have this wind and solar have got various advantages. One of them is it is free. You don't have to pay for it. It is inexhaustible. It will not finish. It will not diminish. And you will always get the sunlight. You will always get the wind. It is available in large part of the world. Our country, India, it also is available abundance of sunlight. Wind energy, it is in some areas, not everywhere. Another, it has got no or very low pollution. And so if you are converting from solar energy to electrical energy, it doesn't create any pollution level. It has got very low maintenance because in solar PV, we don't have any moving part. So maintenance is very low. Operational cost is very low. Solar energy basically can be utilized in two ways. One is solar thermal, and another is solar photovoltaic. Solar thermal is is taking the sun energy and converting it to heat energy, basically. And there are different types of thermal energy power plants and techniques available. What we will be concentrating in this webinar is solar photovoltaic. What the solar photovoltaic panel does, you have seen in many areas, even in your nearby, wherever you are living in India, you might have seen, we have in Lucknow, in our university also, in different parts of the India you move, and different parts of the world, you might have seen these panels, which are showing right hand side of the solar photovoltaic. These panels are connected there. These are basically, their technical name is solar photovoltaic. And this photovoltaic is comprised of two words, photo and voltaic. Photo means light and voltaic means electricity. Photo means light and voltaic means electricity. So it is basically converting light energy into electrical energy. Okay. You sir, am audible?
Yes, sir.
So basically it is, so two types of energy. So basically, these are the two methods in which we can utilize the solar energy, either by solar thermal or solar photovoltaic. Solar is converting solar energy into heat energy, solar thermal, and solar photovoltaic is converting solar energy into electrical energy. It has got various applications in various areas, and in this slide, I tried to show it by using different pictures, because if you see the pictures, it is easy to remember. I have tried to put more pictures in my slides. Here you can see the grid application part. This the electricity which we are getting from the solar PV. There are basically two types of system available in solar PV. One is standalone system, in which we are generating and consuming it, connecting it to the load, and people are utilizing it. This is called standalone system or off-grid system. Another one is the grid application system, in which we are either taking from the grid or giving it to the grid, both ways. If we are having surplus of energy, electrical energy, we can even give it to the grid. More and the top right, you can see the space application. In that, we can see the spaceship, the spacecraft which used to fly in the atmosphere. They have solar panels on their body, and these solar panels convert the solar light available there into electrical energy, and with that help of which we can travel in space also. It's a very good application of solar PV, and it helped the scientists a lot. Similarly, we can see that in transportation system, you have seen the solar cars coming up. Then they are using in agriculture areas, very suitable for places in India where grid supply has not reached, or the supply is very intermittent and we are not getting the suitable supply there. This solar panels helped a lot people in agriculture areas, because it is one type of distributed energy distribution generation, where in according to our, because in the area which we are not able to supply the grid supply, we can have the solar PV panels there, and according to the rating of the load, we can have the generation from it. So very helpful in India in the agriculture sector. And similarly, in residential and health areas, in hospitals, we have solar panels there, where we need we have got the rooftops, and these rooftops have abundance of rooftops available in those areas, and we can have solar panel rooftops, and that can be utilized to generate electricity there. So we can have both electricity there, on grid and also off grid. So this have, and many more applications are there of solar PV, and so it has got lot of applications, lot of users, and it's very easy to have. So, talking about the solar potential in India, what we are having a solar potential in India, this is the data of 30/11/2018, and you can see still the major portion is of coal. The steam power plant, the thermal power plant, which are having major portion is from that, then from the gas, and we can see RES, renewable energy resources, which have got this much portion. They are growing up slowly, and this is the 2018 data. In the service is the data of 2020. This is the latest data which is available in the net. It's of 31st March 2020, and we can see here different installed capacity in India, and this is the difference they have taken. So this is the solar power. You can see it is also increasing year by year. So, and different, still majority is of coal, and we are trying to go for renewable energy sources, and especially in India, we are focusing more on solar power. So we can see how it is increasing, and this is the effect of many initiatives taken by the Indian government. Indian government has a Ministry of New and Renewable Energy under Government of India, is dedicated to planning, development, research, and implementation in the area of renewable energy. We have got a dedicated ministry for it, Ministry of New and Renewable Energy Resources. And we had the National Solar Mission. This was an ambitious project to generate 20 gigawatt of electricity, and out of this 20 gigawatt, means we have got solar thermal and solar PV. 70% would have to be now from solar PV. But this is the National Solar Mission. I will telling you about this slide a little bit more coming here. National Solar Mission. This was the government. This was an initiative from the government of India and the state governments of India to promote solar power. and it was first started by ex-Prime Minister Manmohan Singh on 11 January 2010 with a target of achieving 20 gigawatt by 2022, and which was later increased to from 20 gigawatt to 100 gigawatt by our present Prime Minister, Honorable Narendra Modi. So he increased the target from 20 to 100 gigawatt. This is from solar only, not from all the renewable resources. And you would be pleased to know, and it has been this target which we have already set for 20 gigawatt. We have achieved it 4 years before. We have set the target of 2022 deadline, which was achieved much before that. 4 years previously, we have achieved this target. Now we are having a new target, which is of 100 gigawatt. 100. So you can see in this graph, this is the actual installed capacity, and this is the targeted ones. And we have to reach over here. By 2022, we have to reach about the 100 gigawatt consumption from generation from solar. So this is the government is also pushing this and giving much initiatives and subsidies for this solar, and they want we should go more in solar. So Indian government is also helping us in this area. There are different projects which are being run in India. The Charak solar power, Gujarat, megawatt area, and this you can see how much land it is consuming.
Sir, एक minute. I will request every student to please mute their mic. बच्चों mic mute कर लो please. बच्चों माइक म्यूट करो. फैज अहमद खान, मृत्युंजय सिंह, माइक म्यूट करो.
मृत्युंजय माइक म्यूट.
Okay.
Pranav Verma, please.
Students, please mute your mic. ठीक है sir, let's start.
So we have this Charak solar power. This is in Gujarat, and it is a 750 megawatt solar PV plant. This is in Riva. So you can see how global increase in the solar PV installed capacity. And in this, see you can have in 2015, the position of India is here. First is China, Germany, Japan, US, Italy, UK, France, Spain, and India is in bottom, and then the rest of the countries. And by 2020, we have moved to the 4th place. First is still China is leading, US is second, Japan is third, India is fourth, and we are pushing for further advancement. So Indian government and Indian is much focusing on this, and we have increased from this below rank to the 4th rank in the installed solar PV installed capacity. For the students, job is important, and so we can see how the jobs are related to this area. There are a lot of jobs available in solar, hydro, wind, and solar is leading among this. All this are renewable energy sources. Solar, you can see 2.8 million jobs available in the world. This is data of 2015. So there are a lot of jobs in this area, a lot of research is going on in this area. So what are the challenges? So we have seen how we are focusing. Why are the reasons which have made us to focus on the solar PV, and our government is helping us. But what are the challenges which we are facing? First one is the efficiency. The efficiency of the solar panel is very low. It is the latest is approximately 28% or 30%. And to increase the efficiency of this solar PV, various methods have been employed. One research goes in the area of the material which we are using. The material generally used is semiconductor material, and the physicists they area and they got the types of silicon materials or the semiconductor materials, and the combination of various semiconductor materials which will give us more efficient solar panel. So What you can see, the solar PV system, the smallest part is called the solar cell. The smallest part, in which you might have seen the solar panels, the smallest part is called the solar cell, and these are connected in series and parallel to form solar modules. These modules are again connected to form solar panels, and these panels are connected together to form a solar array. So this you should know. The smallest is the solar cell. These are connected in series and parallel to form a solar modules. These modules are connected again to form a solar panels, which are again connected together to form a solar array. From solar cell to solar array. And then the whole solar system has got many parts that you can believe now. These are different semiconductor materials available which the scientists are working on. The crystalline silicon solar cell and thin film solar cell, concentrating solar cells, and different types of they are working on. And they have got different efficiencies and different working areas. The second challenge is the cost. We have to it has got because people have to ultimately pay it for the solar PV generation, and if we compare it with the present the electricity which we are consuming, especially the coal thermal energy and other, the cost is a much factor. Cost is still now, it has decreased from 1977 till now, but still it is high compared, and we are working on different areas how to reduce this cost by changing the materials or by using different techniques, which is one of them is known as MPPT, maximum power point tracking system. These are used basically to reduce the cost. We might discuss it in coming slides in PPT. So, PV as an option. So, the present trend in electricity generation is shifting from conventional energy sources to non-conventional sources. PV power system has the advantage that the installation is static. It has got no moving parts. Because in all the other thermal power plants, we have got the generators, and in which we have got the rotors, and they have got the moving parts. Here we have got no moving parts. Most of the power plant had got the synchronous generator or the alternator, and they have got the moving parts. And when we have got the moving parts, then the efficiency is reduced. So here, one of the most major advantages is installation static. It has got no moving part. It is very simple and compared to other renewable energy sources. And then they've got longer lifespan. They become 20 years and increase up to 25 years nowadays. And its operational cost and maintenance cost is very low, and it is very significant solution in remote areas. As I've discussed already, it is very significant solution in remote areas where we are not able to get the grid supply. So basically, what are photovoltaic cells, which you have seen in the figures previously? Photovoltaic cells are basically a semiconductor materials which have weakly bonded electrons, and when the solar energy strikes the valence band, then the electron jumps from the one band to another band, and the electron flows. And when the circuit is completed, and the load is connected, the electron flows, and we get the output. The PV gives us the output of the PV panel is DC. It is not AC. This is to remember that the output of PV panel is DC and it is not AC. This is the basic PV cell model. There are different types of PV cell model available. Basically, there are three types of. One is simple, one is moderate, one is a complex one. Here I'm showing one of the model of PV cell. Here is the IG. IG is the current generated when the sun light strikes the panel. And then we have got the different types of elements in that. ID is the diode, then RSH is the shunt resistance, and RS is the series resistance. And these are due to different factors. Because when we design the PV cell, then we have to use the semiconductor materials, and then there are contacts which are joined together, and then the metal grade. All will have the resistance. So this resistance is by RS. Then there will be some leakage current, which is shown by RSH. Then there is some other leakage also that is shown through ID. So this is the basic PV cell equivalent circuit. The output which we are getting is IPV, and KCL. Almost everyone will be knowing that, even the class 12 students and BTech students, all will be knowing the KCL. The output Kirchhoff's current law. So this IPV which we are getting is nothing but IG minus ID minus ISH. It is okay. IPV is nothing but IG minus ID minus ISH. So we're writing this equation. See, IPV which we are getting is IG into NP. I will telling you about NP. Then this is ID current. This ID diode current. It is, diode current equation is this. This is multiplied again by NP, and this is the ISH. ISH this voltage across this RSH divided by RSH. We'll get ISH. So if we apply KVL over here, we'll get this voltage, this VPV divided by RSH. This NP is number of cells in parallel. So if you have to increase the current rating, we add number of cells in parallel. And if you have to increase the voltage rating, then the cells are added in series. So here with the current, I have multiplied it with NP. NP is nothing but number of cells connected in parallel. This Q is the electron charge, A is the identity factor of the diode, A is the Boltzmann constant, and T is the temperature. Okay. So with the help of this equation, we model our PV cell. This is the output characteristic. If we plot power versus voltage and power versus current, we'll get this graph. Here we can see the power is changing with respect to voltage. In the first graph, left hand side. In the second graph, you can see the power is changing with respect to current. And we can see power is first increasing up to a point, and then after that it is decreasing. Similarly, in the case of current, power is also increasing initially, then after that it is decreasing. So this, as an engineer or a scientist, our main aim, or basically as an electrical engineer mostly, or electronics engineer, our aim is to track this power, this maximum power which we are having at that point. We are VMP, this point I'm talking about. This is the P max, it's called, and that point we are having a voltage. That voltage we measure at VMP, voltage at maximum power. Similarly, in this graph, you can see this is the maximum point of maximum power, and at that point we are having the current IMP, current at maximum power point. So these 2 points, VMP and IMP, is of much importance for researchers who want to track the maximum power. This VMP and IMP are taken as a reference point. This is the case of, this is normal PV curve we have seen. This is normal PV curve, and this is the case where of partial shading. Sometimes there is a shade falling on the PV panel. It might be due to the nearby trees or nearby building, or might be due to the shade of one panel falling on the other panel. At that point, we will not get this previous simple curve PV, but here we will have got various maximums, not a single maximum, but we will have got various P points. And among these points, we say the maximum point as a global MPP and the others as a local maximum power point. And among the different maximum points, different peaks, we have to track this maximum power point. So this point is called global MPP, global maximum power point. This is the case of partial shading. This is a special condition when shade falls on the PV panels. So the output of PV panel basically depends upon 2 factors. One is called the solar insolation, and another is temperature. Solar insolation is light falling per unit area. Solar light falling per unit area, that is watt per meter square we measure as. Its standard value is 1000 watt meter per square. And we can see as the solar radiation insolation level is changing, right? We can see the graph is shifting its position. When it is 400, its position is this, and when it is 600, 800, 1000. As the insulation is increasing, the current level is increasing. One thing to note over here is this: with the change in insulation level, the change in current can be seen, and it is clear. There is not much appreciable change in the voltage. Voltage almost remains constant; it has not changed much, but there is appreciable change in the current. So with the increase in solar insulation, the graph is changing. And similarly with this change in temperature, we can see with the change in temperature also the graph is changing. here there is not much appreciable change in the current, but there is appreciable change in the voltage. Here you might see it is a webinar. We cannot have two-way talk. So you can see, because the question arises that when we are having the highest temperature, the 55 degrees centigrade, the graph is the voltage is less, and with the temperature decreases, the voltage is increasing. So one question arises: in which uh, season we will have got the maximum output from the PV panel? Or India, you must say one question may arise from January to December in our whichever locality we are staying in India. What is the in which month we will get the maximum power? Some might say it is in the month of June, March, April, which we are having the summer season. But basically, the output is maximum when we are having the highest sunlight and temperature is low. So in the month of, let's say, February or March, when there's sufficient sunlight and the temperature is less, or in the month of, you may say, October, November, where the sunlight is sufficiently available and the temperature is low. This is there is a physics derivation behind this. Why this happens? That with the increase in temperature, we have got less output voltage. Okay, so it's not the summer season which you have maximum sunlight. It is the time when we are having a maximum sunlight and the temperature is less. We get a maximum output from the PV panel. This was the IV curve. There are two important curves in the PV panels. One is IV curve and then the PV. We have seen previously. This is PV curve. Shape is this PV curve. Another is important is IV curve. So basically, two curves we see for a PV panel characteristic. One is the PV power voltage and the IV current voltage. This is the graph of this previous was the IV characteristic. This is the PV characteristic, and we can see here similarly how will the change in the insulation as the insulation is increasing. As the insulation is increasing, the PV is increasing. Similarly, you can see the insulation is increasing, the output PV is power is increasing. Similarly, with increase in temperature, so this is decreasing. As the insulation is decreasing, output power is increasing, and with the decrease as the temperature is increasing, the power is decreasing. So, if we want to have this PV cell design, we have seen now we can how to model it on MATLAB platform. So we use a MATLAB software is there for first year student might be not knowing, but highest year student might second year, third year if they are joined, they might be knowing about this MATLAB matrix laboratory software. So what we see, this is the circuit of the PV panel. Here we have in that circuit which I have shown previously, there was a series resistance, shunt resistance RSH, and the output we can neglect it in designing, and we have considered a simple circuit. Here I see the output, and which is IPH minus I naught. IPH is the current generated, I naught is the diode current. So IC which we are getting here, again you apply KCL, that IPH minus I naught is equal to IC. So IC is equal to IPH minus I naught, and this is the diode equation I naught. Okay, and if we rearrange this equation, we have this equation VC, the output voltage we are getting, AKTC by Q ln IPH plus I naught minus IC by I naught minus ICRS. So this is the equation which we use for modeling of the PV cell. V is equal to AKTC by Q ln IPH plus this equation. This we use for the modeling of the PV cell. And this parameters I've already discussed. This A is dielectric factor, B is K is Boltzmann constant, T is temperature, Q is the charge, and IPH, I naught, IC is the different currents flowing in the circuit. This IPH, I naught, IC. These are different currents which are flowing. So we can use this equation to solve our equation. As I've already discussed, the output of the PV panel depends upon two parameters. One is temperature and two factors basically. One is temperature and one is solar insolation. So here we have used this equation. This equation has been taken from the paper of Altas and Ashraf, which was published in IEEE Econ Journal. It says that the output depends on two parameters, voltage and current, and they have derived this equation. So this CTV is basically change in voltage due to change in temperature. And we have just used this equation. Then CTI is the change in current due to change in temperature. So the effect of change temperature, both the voltage equation and the current equation has been considered by CTV and CTI. Similarly, CSV and CSI is change in voltage due to change in solar insolation, and CSI is change in solar insolation. So change in current due to change in solar insolation. So what will be the change in voltage? That will be CTV into CSV. Change in voltage due to change in temperature and change in solar insolation due to change in voltage due to change in solar insolation. So what will be CV? CV will be nothing but CTV into CSV. Both for change in voltage will be calculated by both CTV into CSV. Similarly, CI, change in current, that effect is also by CTI into CSI. So multiplying this, we will get the equation CV and CI, and that can be that we will get, and that will multiply in this equation BCS. So we'll get the final voltage and the final current from the panel. And all this equation, first equation, this equation, BC is equal to AKTC by Q, IPH minus I, last equation. Then these two equations, CTV, ETI, this CSV, CSI, this four equations, and finally this equation. All this equation we use in the modeling of the PV panel. This is the final simulating model of a PV panel cell we can see, and I have considered this model, and in this, this is a slider block with which we can vary and see the effect of change in solar insolation. If we vary the solar insolation, we can see its effect. Similarly, to see the change in temperature, we can use this slider block again and change the temperature and see our reading. This is the workspace which we have used workspace block to save the result. If we double click this ball while designed and you open this, you will get this one. In this, we have got again this block which are connected together. One is the PV cell equation block, other one is the CV and CI calculation block. Which are these four equations which we discussed here, these are in this block, and the previous first voltage V is equal to AKTC by Q on IPS plus I naught minus IC. That equation is in this PV cell equation block. If we again open this block, this is this block, PV cell equation block. If we open, we'll get this block. And the voltage equation you might have seen AKTC. See, this is A, right top. This is A. This is K, Boltzmann constant. TC, temperature is added 273 to convert it to Kelvin, and they have both have A into K into T. TC, they are multiplied and divided by Q, charge of the electron 1.602 into 10 minus 19. Charge of the block, electron, we have divided it, and then again ln of IPH plus I naught minus IC, plus minus IPH plus I naught minus IC we have used, and minus after that we'll got ln, and this is multiplied with this minus ICRS. So basically this is this block is this equation. BC is equal to AKTC by Q. This equation has been simulated in MATLAB by this equation, this model. Then this model's calculation of CV and CI, this effect have been taken here. This is CTV. That equation, all CTV, CTI, CSV, CSI has been calculated. You can see TC minus TX into beta 1 plus beta into TC minus TX. We are getting this CTV. Similarly for CTI, CSV, CSI, all these four equations have been modeled there. Here. After that, for CV, as we have discussed, what is CV? CV is CTV into CSV. CTV into CSV, we get CV. And for CI, we get CTI into CSI, we get CI. So similarly, here we can able to get CV and CI. Uh, So this is basically the model of the PV cell. And if we select all and we create subsystem, we'll get finally this model. Now, when we run this model, the output which we are getting is C. By varying the temperature, we have seen, as we have increased the temperature from 20 to 40, the voltage level has decreased as we wanted, as we expected. That if we increase the temperature, the voltage level should decrease and current remains almost constant. Similarly, for this is all the simulation results of the MATLAB. Similarly, if we keep on changing the solar insolation, we can see here that current is increasing and voltage is almost similar. So with both the effect have been considered, effect of temperature as well as solar insolation. In this, I have kept the solar insolation constant and varied the temperature. In this, I have kept the temperature constant and varied the solar insolation, and the graphs have been plotted. For plotting this same graph on the MATLAB, we use the command hold on. Hold on graph is used for calculate for this. For using this, hold on command is used. And similarly, I've plotted the PV curve. PV curve here I've got insolation I've kept constant and varied the temperature, and you can see as the temperature decreases, then output is maximum. For 50, we have got the minimum power among this power, and as the temperature decreased, the power has increased. Similarly, if we keep temperature constant and vary the solar insolation, the output has increased. So this is the PV characteristics which we have plotted. Like one we have kept the insolation constant and varied the temperature. In another, we have kept the temperature constant and varied the solar insolation, and results were as we expected. So this was basic about the solar PV modeling. One more thing I would like to add in this is how to track the maximum power. As I've already discussed, this is the maximum power which is there, and we want to track this maximum power. So there are basically two types of tracking available. One is mechanical tracking, another is electrical tracking. Mechanical tracking is mechanical rotation of the solar panel with the according to the sun, according to the season, according to the location. We have got different type of tracking system, and LDR and GSM are used in that, in single axis tracking and dual axis tracking. We keep on rotating our panel according to the position of the sun. This is one of the methods to track the maximum power. Generally, it is not done. Generally, because it also consumes energy, because we have to keep on rotating the panel with it. So, are you able to see the PPT?
Yes, sir.
So basically what we do, another is this is mechanical tracking, another is the electrical tracking, and we have what is we are use power converters and the sensing devices which are connected to calculate the maximum power. As I discussed in my earlier slides, in the PV curve and I curve, I showed 2 points, VMP and IMP. You might be remembering during the starting of the lecture, I discussed VMP and IMP. That point at which we are having the maximum power. So these points are used as the reference to generate the signals to have our maximum power. So how MPPT works? This is the main aim of MPPT is to make the PV module operate at that point, IMP, VMP, which are the reference point. And these are done by, we are having a DC to DC converter. As I've already discussed, the output of the PV panel is DC. And so we use a DC to DC converter to track that maximum point, VMP and IMP. So if we are using VMP as the reference, then this, and we are having a feedback controller, because we are having to track the maximum power point, so we have to have a feedback system. So for that, we are having a voltage, that system in which we are having the VMP as a reference, that is known as voltage feedback control system, in which we are using the V reference as the feedback. And if you are using IMP as the reference, then it is called a current feedback control system. If you are using a voltage, then it is a voltage feedback control system as a reference, and if you are using current as a reference, it is called a current feedback control system. So these are basically the there are lots of MPPT algorithm available in the literature, and which are being developed also nowadays. And the patent, I'm also having one of the patent for this MPPT algorithm itself, so which have been granted recently. Uh, so I want to discuss basically there are four. I will tell you in short. These are the four basics which commonly used algorithm. First one is called the perturbed and observed method, P&O method. I'm taking you to a curve of PV. Say we are taking a simple PV curve. This curve you see. We are taking a PV curve. This is the BMP and IP I was talking about, the reference point. See, if you want, we have to track this maximum power point. So there can be different ways. First is perturbed and observed method. What we do in that method, we take a voltage Vk. Suppose it is here. You are able to see the mouse. Here it is Vk. Between 5 and 10 we are having at this point Vk, and that at that point we see the power. Let it be Pk. At Vk we are having the power Pk, and if we are slightly perturbing and we are increasing the voltage, Vk plus 1, this from it is 6, it has increased to 7, or you can assume we have to Vk plus 1, and we can see the power Pk plus 1. And that time power will be Pk plus 1. First you have taken the power Vk, the power K. Then voltage Vk plus 1, whether the power Pk plus 1. If we subtract Pk plus 1 minus Pk, Pk plus 1 minus Pk if we do, then the power which we are getting will be positive. It will be greater than 0. As we are on the left side of the slope, so power will be positive. It means we have to increase the voltage to get this VMP. If we are on this side of the graph, then if we do that measurement Vk and K and 30 Vk, get it. So this means you have to decrease the voltage, and at the maximum power point Pk plus 1 minus Pk will not be exactly 0, but will be approximately equal to 0. So we give a error value of 0.0, you can say, and say if the Pk plus 1 minus Pk in this range, then we have achieved the maximum power. One method is this. Another method is that this is called perturbed and observed method. Another method is incremental conductance method. In this, what we do, we measure the slope here. In this side, dp by dv. If we do dp by dv, it will be greater than 0 in this side. And dp by dv will be less than 0, will be negative here. At the maximum power point, dp by dv will be equal to 0. So we can get the maximum power point accordingly. In the third one, constant voltage or open circuit voltage method, what we do, we can see that the voltage at which we are getting maximum power point is closer to this point, and this point we can see the voltage is something and current is 0. The power is 0, voltage is 23. We say the current will be 0. So current is not flowing. It means it is an open circuit. So that point is known as VOC. That voltage is called VOC, and this VMP is closer to VOC, and it is told that it is between 0.72 to 0.8 of VOC. If we want to calculate VMP, then we can, if we calculate VOC, open circuit voltage, multiply it to 0.72 to 0.8 is the range, and this it will be 0.72, 0.73, 0.74. It depends upon the material of the PV which we are using. So with the help of that, we are able to calculate VMP, and after that calculating VMP, we are able to track the maximum power point. So these are basically the three methods: perturbed and observed, incremental conductance, and open circuit voltage or constant voltage method. And all these methods have their advantage and disadvantage. It will be there, yes. So this method is hybrid method, and in which we can combine these any two methods. For example, if you combine this open circuit voltage method with the perturbed and observed, if we use open circuit voltage, calculating VMP by 0.72 of VOC, then we will not get the exact VMP. To get the exact VMP, then we will be using the perturbed and observed method to get the exact position. So two methods can be combined also. This is called hybrid methods. So all methods have got the advantage and disadvantages. But before designing the MPPT, some factors we have to see that what are the factors which our algorithm will have. One will is the dynamic response. Means we are able to achieve the maximum power very fast. If we are at the lower part of the graph, we have to reach at P max. It should be very fast. It should not be slow. But the much time will take, the loss will be there. Another is steady state response. After reaching the maximum power, it should not oscillate there. If it keep on changing, then we will not have, then there are oscillation losses also. As a rapidly changing atmospheric condition, time is not there, so it is lengthy, that in rapidly changing atmospheric condition, some of the logarithm fail. Because the condition changes very fastly, the algorithm fails. And lastly, it should be simple. Last point I want to discuss is comparing these algorithms. See, perturb and observe method, the first one, in which we used to calculate VK and P, VK, PK, VK plus 1 and PK plus 1, subtract and compare. So it takes time. So it has got slow response. And in this constant voltage, we calculate VMP just 0.72 of VOC and we get the VMP, so it is the fastest among the three. And incremental conductance is in between the first and second. Steady state response is oscillation around MPP, but and also will have some oscillations. Why? Because it will keep on PK plus 1 minus PK will keep on doing even reaching near about MPP and we will have losses. There's two methods. You're directly calculating the VMP, so there will be no losses, no oscillation both. This one is simple to implement. This is more simple. This is relatively complex. Efficiency in these two are good. In this we have got very low efficiency. Cost wise, if we say pattern was less costly, this is more costly. This is the costliest. Why it is costly? Because to see this, if we calculate the VOC, VOC is open circuit voltage, and for calculating the VOC, we have to disconnect the load. To calculate the open circuit voltage, what you have to do, you have to disconnect the load. So if we disconnect the load, what will happen? There will be loss. You will not be supplying the energy, and you have to calculate. And you have to do this because you have to calculate VOC. So what the researchers did, they added a pilot panel in parallel to of similar nature, of similar rating from the same company, and they added this in parallel to calculate the VOC. So adding of the panel is good, that we are not, the supply is not getting interrupted, but it is making the system complex. So this is, and my patent is on this part only. What we have done, we have replaced the pilot panel with a microprocessor. Then the third, and this is rapidly changing. Here we have got no tracking system, so it doesn't fail. It fails, and this tracks in the right direction. X factor, that what will be the value of the K, means how much value will multiply into the VOC. It will be 0.72, 0.73, 0.74. It is very tough to choose. I have told that it depends upon the material, but it is tough to choose which material we are using. Okay. So till now, I think so. This is enough till now. Okay, madam.
Yes, sir. Thank you,
Minutes are
sir.
remaining.
Thank you, sir. So now the floor is open for the questions. Any question? You may raise your hand and I'll unmute the mic.
How to the raise hand? If they know.
Yeah,
How to raise hand? Someone
yes,
might be
they
not.
can. They can. Yes. Yes, Prateek. Ask.
Ma'am, there is one more major drawback of solar energy, that a solar panel consumes a lot of space. So, as sir said, it costs a lot. So, even if a poor family manages somehow to purchase a solar panel, but he will not be able to install it because of its space. So isn't there a ways that we can modify the solar panel so that it can occupy less space?
Yes, space is a problem. You are right. So ultimately, if you have to, as I've discussed, there are two challenges. One is the efficiency, one is the cost, and they two are these two are related to the space also. If you have, if we increase somehow the efficiency of the panel, and if efficiency is increased, then from even a small panel will have higher output, and then we can manage it. And this is what the scientists are working on to reduce the space, and which will be ultimately done by increasing the efficiency of the panel. Okay.
Okay, thank you, sir. You can raise your hands by clicking the reactions. You can see in the bar below, reactions is there. You can click here and you can raise your hand from here. So, any more questions? Any more questions? No questions?
No, ma'am.
No, ma'am.
Okay. Okay. Raksham, you want to ask something?
No, ma'am. All
Okay.
good.
Okay. Okay.
Thanks for the webinar.
Okay. Thank you.
Thank you, sir.
Let me thank.
Sure, ma'am.
Thank you, sir, for the enlightening session. And I hope all the students must have enjoyed it. And in these testing times, sharing knowledge is the only motivation that will keep us going. So thank you so much. Department of Electronics and Communication from ILM College, thank you, and thank all the participants for this lovely session. Thank you. So I am ending the meeting. Okay.
Okay, ma'am.
Thank you.
Thank you, Dr. Asim. Thanks. I'm ending the session now.